In this video, we'll introduce the monotone convergence theorem for sequences. Now first, a couple definitions. A sequence A sub n is bounded above if there is a number m such that each term in the sequence A sub n is less than or equal to m. Similarly, a sequence A sub n is bounded below if there is a number m such that each term in the sequence A sub n is greater than or equal to m. Now, a sequence A sub n is simply bounded, or so is bounded, if it is bounded above and below. Now, first one theorem, which states that if a sequence A sub n converges, then that sequence A sub n is bounded. So we know if it is a convergent sequence, then it must be a bounded sequence. If the sequence A sub n is unbounded, then that sequence A sub n diverges. So there's no way that it converges into anything if that sequence is unbounded. Note, this theorem does not imply that all bounded sequences converge. For example, if you have that sequence -1 to the n from 1 to infinity, that is bounded because it's bounded below by -1, it's bounded above by +1, but it diverges because it doesn't converge to one single number. Now, a couple other definitions. A sequence A sub n is increasing if A sub n is less than A sub n plus 1, so that each next term is greater than the previous term. A sequence A sub n is decreasing if A sub n is greater than A sub n plus 1, so that each next term is less than the previous term. Now, a sequence A sub n is monotone if it is increasing or if it is decreasing for each value. So if it's always going up, then it's monotone, or if it's always going down, it's monotone. So it could be increasing or decreasing, but it has to be one of the two. Now, the monotone convergence theorem states that a bounded sequence A sub n that is monotone converges. Note, this theorem does not give a method for actually obtaining the limits. It only tells us if a limit exists. So if we have a sequence and that we show that it is both bounded and monotone, then it is a convergent sequence. Let's look at an example. Determine if the sequence 5 to the n divided by n factorial from n going from 5 to infinity converges. So we need two things. So we need to show that if it's bounded and if it's monotone, then it will be a convergent sequence. So let's first consider the ratio A sub n plus 1 divided by A sub n. So the A sub n plus 1, that's 5 to the n plus 1 over n plus 1 factorial. A sub n is 5 to the n divided by n factorial. So if we divide those, we get 5 to the n plus 1 over n plus 1 factorial divided by 5 to the n divided by n factorial. And then if we simplify that by multiplying the numerator by the reciprocal of the denominator, that's equal to 5 over n plus 1. And then for values of n which are greater than or equal to 5, the 5 over n plus 1 is less than 1, which means that this is a decreasing sequence for n values of n greater than or equal to 5. Now, one thing to note, we see that the terms are decreasing, but they're also always positive. This means the sequence is bounded, because we could say it's at least bounded by 0, because it's always going down, but it's also always positive. Because it's bounded below by 0, and it's bounded above by, well, if you plug in the first term, which is when n is equal to 5, that would be what? That's 5 over 6, so that the largest term is 5, 6, because it's always going down afterwards, and it's bounded above by 5, 6, and it's bounded below by 0, so therefore it is a bounded sequence, and we know that it is decreasing, so it is monotone. So by the monotone convergence theorem, the sequence converges.